Hi everyone, I'm Ruize Tang from Nanjing University. Today I will be presenting our work, Converos, which focuses on practical model checking for verifying Rust OS kernel concurrency modules. This work was done during my internship at Ant Group. Our work centers on ASTERINAS, a Rust-based Linux-compatible open-source kernel that is actively maintained and has grown to over 100,000 lines of code. It is designed with a focus on high reliability. However, even with Rust safety guarantees, concurrency correctness remain notoriously hard. Bugs like deadlocks or data races still arise due to flawed designs or logical errors, which can lead to severe consequences like kernel panics or harms. To address this work adopts model checking, a formal verification technique that exhaustively explores all interleavings of concurrent executions. Compared to testing, it is more effective at uncovering corner case concurrency bugs. Model checking has proven practical in industry. We apply it to verify concurrency modules in ASTERINAS. Applying model checking to a real OS kernel is hard. First, writing a high-quality spec is challenging. Kernel code is low-level and tricky, and formal modeling requires expertise. If the spec isn't well designed, model checking easily hits state explosion. Second, checking that the spec accurately reflects the implementation is non-trivial. Discrepancies often arise due to modeling errors or code changes. These discrepancies can cause both positives and negatives, reducing the confidence of the verification. To address this, we developed Converos, a practical model checking methodology. It follows a simple three-step workflow. First, write a spec. Second, check conformance using execution traces. And third, run model checking to find correctness property violations. We applied Converos to 12 concurrency modules in ASTERINAS OS and found 20 real bugs, including deadlocks and data races. Despite the complexity, the whole effort took only 4 person-months, with a low spec-to-code ratio. What makes Converos practical is a modeling approach that makes formal specs easier to write and verify, and a conformance technique that handles incomplete logs. Now, let's briefly walk through Converos. It follows a 3-step workflow. In step 1, we write formal spec in PlusCal. These specs are structured in a multi-layered, multi-grained approach to make modeling easier and more scalable. In step 2, we check if code execution traces from kernel modules conform to the spec. We developed an enhanced trace validation technique that is robust to imprecise logging and easy to use. In step 3, we perform model checking to verify correctness properties. If violations are found, we write tests to reproduce them in the code, apply fixes, and re-verify. The first step in Converos is writing specs. To manage the complexity of writing specs for OS concurrency modules, we adopt a multi-layered spec approach. It contains high-level specs and low-level specs. High-level specs captures the design intent of synchronization primitives by specifying the expected behavior of public APIs like lock and unlock, while abstracting away how they are implemented. This makes them easier to write and verify, and allows early conformance even before modeling low-level internals. They also provide a basis for developing low-level specs later. After high-level specs, we build low-level specs that closely reflect the implementation. These are written by translating Rust code into PlusCal. Since PlusCal has an imperative syntax, the translation is relatively straightforward for programmers. We model key operations such as atomic actions using labeled blocks in spec. For example, the figure shows the code segments in different kernels. Each kernel block corresponds to multiple labeled actions in the specification. We also explicitly model Rust-specific semantics, such as automatic lock release triggered by job. When a guard goes out of scope, the red block in the figure illustrates how this behavior is captured. When writing low-level specs, we need to carefully control granularity. Too fine-grained granularity causes state explosion, while too coarse may miss bugs. We So we adopt a multi-grain approach. For basic primitives like spin-locks, we write fine-grained specs. For modules built on top, we reuse verified behavior of these basic primitives and caution the internal logic as atomic actions while preserving key interactions. This ideally follows an interaction preserving principle to retain correctness, which avoids redundant modeling and improves checking scalability. As shown in the figure, build-text lock internals uses a spin lock. In this spec, we model it as a single atomic variable, that is, with a lock, which captures the synchronization effects. Next, we perform conformance checking to bridge the gap between the spec and the code. In TLA Plus, this can be done by either generating spec traces and replaying them in the code, or by collecting code traces and validating them against the spec. Since OS concurrencies are hard to control for replaying spec-generated traces, we use trace validation, which require only lightweight logging in the code. To perform trace validation, first, we collect execution traces from the system. We develop the test harnesses and add logs to the code to capture actions described in the spec. Our trace validation framework then runs the test harnesses with random interleavings and collects concurrent logs, which are sorted by timestamps. Each log includes timestamp, process ID, event name, and relevant variable updates, such as the PC variable that tracks the control flow. These logs act as constraints that guide the matching process during trace validation. Trace validation uses a specially constructed trace spec based on the original specs, serving two key roles. First, the trace spec extends the original spec to explore its state space. Second, it constrains allowed actions based on the observed code trace logs. During validation, the trace spec reads the trace logs and applies constraints like process ID, event name, and variable updates. The model checker then explores these actions to see if the traces match a valid path in the spec state space. A failed match indicates a discrepancy, usually a modeling error at a low level or a code bug at a high level where the spec reflects the intended design. In practice, validating execution traces in OS concurrency modules faces two main issues. First, logged timestamps may not reflect the actual execution time. This can lead to out-of-order logs after sorting, making the trace fail to match the spec and causing false discrepancies. Second, logging every action at once can be burdensome and error-prone, especially for specs with many labels. To tackle these issues, we developed an enhanced trace validation technique that supports missing events. We insert a special missing event logs before and after an action, defining a flexible time window during which the action may have occurred. After sorting the log by timestamps, post-processing merges consecutive missing events into a single one, ensuring that the next event is always a non-missing event. The non-missing events then serve as anchors to guide the matching process during validation. This design allows the model checker infer action order within a merged missing event and infer unlogged actions. To support enhanced trace validation, we improved the trace spec to handle missing events. When TLC model checker encounters a missing event, it tries two branches. Branch 1 tries to match the next normal event, just like in regular trace validation. Branch 2 explores currently enabled actions in this missing event without moving forward in the trace. This makes the missing event stay active and match other behaviors in the next step. To make trace validation efficient, we apply two prominent rules. First, we limit the maximum depth TLC can explore from a missing event. Second, we define a convergence point in the post-processed trace. Once TLC reaches that point, it stops further branching for the corresponding missing event. When collecting traces, we avoid logging everything from the beginning. Instead, we adopt an incremental logging strategy. We start with logging coarse-grained events like API calls and gradually add more internal actions logging as needed. Thanks to the missing event technique, validation works even when logs are incomplete. This allows us to detect discrepancies early and reduce logging effort during the development process. Finally, we use TLC to verify safety and liveness properties on the low-level specs, such as mutual exclusion and the absence of deadlocks, livelocks, and starvation. If violations occurs, we convert the counterexample trace into a test case to reproduce the bug in code. If reproduced, we fix both code and spec. If not, we revise the spec for modeling errors. We repeat this process until all checks pass. Along the way, we also fix additional byproduct bugs, such as kernel panics during testing, improving overall reliability. In our evaluation, we applied Converos to verify 12 concurrency modules in ASTERINAS OS, covering about 4,000 lines of Rust code, including synchronization primitives like spinlocks and mutex locks, as well as important thread safety parts like ring buffers. We identified 20 bugs during process. 9 were found through model checking, while 11 were byproduct bugs. The entire verification effort required about 4 person-months. This table summarizes the 20 bugs we found. The first group includes 9 bugs found through model checking, covering a range of concurrency violations such as deadlocks, livelocks, and the violation of mutual exclusion. The second group includes 11 byproduct bugs found during modeling or test case execution. These results demonstrate the effectiveness of Converos in uncovering deep and hard-to-reach bugs in OS concurrency code. This example shows a tricky concurrency bug in the range lock implementation. Developers initially identified a lost wake-up bug during testing and attempted to fix it. However, Converos found that the fix was flawed. After several failed attempts, we finally fixed the bug correctly. Each time we proposed a fix in the specification, Converos verified the fix and conformance, revealing other scenarios causing the bug or new bugs introduced by the fix. This guides us toward the correct solution. Overall, the example illustrates how Converos can expose flawed fixes and ensure bugs are properly resolved. This example shows a discrepancy bug and trace validation in an upgradable reader's writer lock. The code sets the up reader bits and checks the previous lock states. Our spec mistakenly used the current writer lock state. Trace validation exposed the discrepancy. Another thread released the writer lock in between, causing the spec to show a successful lock acquisition, while the code trace didn't. We fixed this spec by storing previous values. This shows how trace validation catches subtle modeling errors. This table summarizes manual effort for verifying each module. Overall, the spec-to-code ratio is low. Writing all specs took around 43% days, and the trace validation added about 21 more. So in total, the entire process took about 4 person-months, which shows that our method is practical for real code. To summarize, Converos combines multi-layered, multi-grained specs and enhanced trace validation to form a practical workflow. It is applied to verify 12 OS concurrency modules and uncover 20 real bugs, demonstrating that the approach is scalable, efficient, and practical for verifying real-world kernel concurrency code. Thank you.